Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over section 1, i.e. the multiple choice questions from the 2021 SQA National 5 Physics exam paper. Now there are 25 questions in this section and I'd recommend that you try them yourself before looking at these solutions. So let's get going. Question 1 says, which of the following is a vector quantity? Well, remember, a vector quantity is one that has both a magnitude and a direction, whereas a scalar is one that has a magnitude or size only. So you'll see from the list here that energy, time, mass and distance are actually all scalars, where we don't care about direction, but force is a vector quantity because we do care about direction and magnitude. So our answer here has got to be A. Question 2 says a skydiver falling from an aircraft reaches terminal velocity because the air is very thin at high altitude, there is very little friction acting on the skydiver, gravitational field strength is less at high altitude, the skydiver's weight is balanced by air friction, or the skydiver is streamlined. Well, if we think about what terminal velocity is, first of all, remember that's a constant speed or constant velocity reached when the vertical forces acting on the skydiver become balanced. So if we do a little sketch here, you can think about this block as being the skydiver, and then they're going to have their weight, W, acting downwards, and they're also going to have a force upwards balancing this weight downwards when they've reached that terminal velocity, and this upwards force is going to be drag or air resistance. So when these vertical forces become balanced, the skydiver will reach this constant velocity or terminal velocity, and therefore we can say the answer is D. The skydiver's weight is balanced by air friction, where air friction is just another phrase for drag or air resistance. Question 3 says a block of mass 5.0 kilograms is placed on a smooth horizontal surface. Two forces are applied to the block as shown. So you'll see here, there's our 5 kilogram block, we've got 25 newtons acting to the left and we've got 15 newtons acting to the right. And it says the acceleration of the block is. Well, because we've got two different forces acting on the block, first of all, we first want to find the unbalanced force F acting on the block. So to do that, we can take the smaller force away from the bigger force and we get 25 minus 15, which gives us 10 newtons. And now because we know the mass and the unbalanced force, we can use Newton's second law F equals ma to find the acceleration. So we can now calculate the acceleration A. So if we use F equals ma, we can plug in the numbers. So we have 10 is equal to 5.0 times A, and if we divide both sides by 5 now to get A on its own, we get 10 divided by 5, which gives us A equals 2.0 meters per second squared. So that gives us the answer of B. Question 4 says a student designs an experiment to investigate the relationship between the extension y of a spring and the magnitude of the force F applied to it. Different masses are attached to the spring and the length of the spring is recorded for each mass. So here's the spring in its rest position before it's been extended, and then by adding a mass to the hook part of the spring here, it's going to cause the spring to extend by this distance y. And it says the relationship between F and y is F equals ky, where k is the spring constant of the spring. And this is actually an experiment and an equation that you see in advanced higher physics called Hooke's law. But in this paper, it's just in here as a skills question. So it says the length of the spring with no mass attached is 0.08 meters. When a mass is attached to the spring, the length of the spring increases to 0.110 meters. The spring constant of the spring is 12 newtons per meter. The magnitude of the force applied to the spring is. Well, this is one of the unseen equations or unseen formulae questions where we need to just use the equation they've given us and plug in the numbers and make sure we're using the correct numbers based on the information. So we're going to use the equation F equals ky, but that means we first need to find the extension y. So what we can do is take our final length of the spring and subtract the initial length of the spring to get y equals 0.110 minus 0.080, which gives us 0.030 meters if you put it into your calculator. And now because we have the extension y and the spring constant k, which is 12, then we can just plug those into the equation F equals ky. So now we can calculate the force F. So we have F equals ky, and we can plug in the numbers to get 12 times 0.030. And if you put that into your calculator, you should get an answer of 0.36 newtons, which gives us the answer B. Question 5 says an arrow is fired horizontally with a velocity of 60 meters per second. The effects of air resistance on the arrow can be ignored. Which pair of graphs shows how the horizontal velocity vh and vertical velocity vv of the arrow varies with time t during the first second of its flight? Well, to answer this, we firstly need to remember that projectiles have both a constant horizontal velocity and a constant vertical acceleration. So that means for the graph of horizontal velocity against time, which is on the left hand side in each of these options here, we're looking for a graph that shows a constant velocity, which is just going to be a straight line going along the way. So that means our answer could be A, because we've got a straight line going along the way, or it could be D, because we've got a straight line going along the way for that one. But we need to see what the vertical velocity is going to do against time as well. So we said that for horizontal velocity, we can say that the initial speed u is 60 meters per second, and that means the final speed v is also going to be 60 meters per second because it's constant. So we're looking at this graph here with the constant 60 meters per second along the way for horizontal velocity. But for the vertical motion, remember we can say that the initial vertical speed is 0 meters per second for a projectile launched horizontally, and we can use the acceleration equation whenever we're dealing with the vertical motion of a projectile. So remember we want to find the final vertical velocity v, so if we plug in our values, we have 9.8 meters per second squared for the acceleration due to gravity is equal to v minus 0 divided by 1.0, because remember we're thinking about motion over the first second. So if we rearrange for v, we can cross multiply here to get 9.8 times 1, which gives us v equals 9.8 meters per second. And notice how this is roughly equal to 10 meters per second. So that means our final velocity in these graphs needs to be at 10 meters per second after the 1 second, which is shown by this graph here and this graph here. However, for options A and B, we saw constant vertical velocity here, so these are not going to be the correct options. The answer has got to be D, where we've got a constant horizontal velocity of 60 meters per second and a vertical velocity that increases up to a value of roughly 10 after the 1 second. Question 6 says a satellite orbits the Earth at an altitude of 540 kilometers. The graph shows how gravitational field strength varies with altitude. So you can hopefully see that with increasing altitude, we have a decreasing gravitational field strength here. It then says the mass of the satellite is 78 kilograms. The weight of the satellite at this altitude is... Well, if we go back to the graph, the satellite we're told orbits at an altitude of 540 kilometers. So to find the weight of the satellite at this altitude, we can use the equation W equals mg, and we have the mass of 78 kilograms, but we don't have the gravitational field strength. So that's what we need this graph for. So if we go to altitude first and look for 540 kilometers, that'll be this part here, 2 boxes along from 500. And then if we go up to the line and then back along to the y-axis, you see we have a value of 8.3 newtons per kilogram because it's 3 boxes up from 8. So I'm just going to put a wee mark there, that's our 8.3 newtons per kilogram. And then we can go on and calculate our weight. So we have the equation W equals mg. We can then plug in our numbers, 78 times 8.3. And if you put that into your calculator, you should get an answer of 650 newtons to 2 significant figures. So that means our answer is C. Question 7 says a student makes the following statements about geostationary satellites in orbit around the Earth. Statement 1 says the orbital period of a geostationary satellite is 24 hours. Statement 2, geostationary satellites remain above the same point on the Earth's surface. And statement 3 says geostationary satellites orbit at different altitudes. Which of these statements is or are correct? Well, to answer this, you just need knowledge of geostationary satellites. So the first one, the orbital period of a geostationary satellite is 24 hours. That is correct, because remember a geostationary satellite will go around the Earth once in the same time it takes the Earth to spin once on its axis. For statement 2, geostationary satellites remain above the same point in the Earth's surface, and that is also true because the period of its orbit matches that of the length of one day on the Earth, i.e. the time taken for the Earth to rotate once on its axis. And lastly, statement 3, geostationary satellites orbit at different altitudes. Well, that is wrong because remember geostationary satellites will orbit at an altitude of 36,000 kilometers above the Earth's surface. So that means we have 1 and 2 are correct, which gives us the answer C. Question 8 says a star is 2.4 times 10 to the 18 meters from Earth. This distance in light years is... Well, remember to convert from meters into light years, we need to know how many meters are in 1 light year. So to do that, we can use speed distance time. So we can do d equals vt and substitute in our speed of light, 3 times 10 to the 8, and then multiply that by how many seconds are in 1 year. So we can do 365 days in a year times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. And that gives us this answer, 9.46 times 10 to the power of 15 meters when you put it into your calculator. So that's how many meters are in 1 light year. So if I want to find out how many light years this distance is, I need to divide this distance in meters by the distance of 1 light year in meters. So I end up with 2.4 times 10 to the 18 divided by 9.46 times 10 to the 15, And if you put that into your calculator, you should get roughly 253, but you'll see that all the answers are given in scientific notation. So 253 is the same as writing 2.5 times 10 to the power of 2 light years, where we've just put that to two significant figures or one decimal place. So that gives us the answer of B. Question 9 says light from a star is split into a line spectrum of different colours. The line spectrum from the star is shown, along with the line spectra of the elements calcium, helium, hydrogen and sodium. So you see we've got the line spectrum from the star at the top, and then we've got the line spectra for all the different elements below it. It says the elements present in this star are sodium and calcium, calcium and helium, hydrogen and sodium, helium and hydrogen, or calcium, sodium and hydrogen. And remember, the key to this kind of question is that if the elements appear in the star, then all of the lines from the element are going to appear in the spectrum for the star. And if you're doing this on paper, you could use a ruler to make it easier to see which lines actually match up. Well, if we start with calcium, you'll see we've got a line here which doesn't appear in the spectrum of the star, and then we've got a line over here which doesn't, so that means calcium does not appear in my star. We've then got helium, which has two lines on the right hand side here which don't appear in the spectrum for the star, so that means helium is not going to be present in the star because there's lines in here which don't appear in the spectrum. And we've also got this thicker line here which doesn't match up with this thicker one in the star. Next we have hydrogen, which only has two lines, so we have this thicker one here which does actually match up with this one in the star, and this thinner one over on the left which does also match up with this middle one up here in the star spectrum. So that means we could say that hydrogen is present in the star. And lastly, for sodium, we have two darker lines here which match up with these two lines in the spectrum of the star. We then have this line here which matches up with this one, and this thicker one which matches up with this one. So that means all of the sodium spectral lines appear in the spectrum for the star, so that means that sodium is also present in the star. So that means we have hydrogen and sodium, which gives us the answer C. Question 10 says a heating element is connected to a 12 volt supply. The power rating of the heating element is 48 watts. The charge that passes through the heating element in 5 minutes is... Well, remember, to calculate charge we need current and we need time. So you'll see we've got a time of 5 minutes which we need to convert into seconds, but we don't have a current yet. But we do have a power value and also a voltage. So let's find the current first of all using one of our power equations from electricity, P equals IV, and then we can sub in the current value into our charge equation, Q equals IT, in order to find the charge. So let's do P equals IV to find what I is. Let's sub in the numbers, so we have 48 watts is equal to I times 12, and rearranging for I, we can divide both sides by 12 to get I equals 4 amps, and then we can use our equation for charge, current and time. So we have Q equals IT, substituting in the numbers, we have 4 amps times the 5 minutes times 60 to get it into seconds, and that gives us the answer 1200 coulombs, which is E. Question 11 says an oscilloscope is used to test 3 different power supplies. The diagrams represent the traces seen on the screen of the oscilloscope. So we have trace X here, this straight line, trace Y, which is a wave, and trace Z, which is another straight line. And it says which of these traces represent a DC signal. Well, remember, DC stands for direct current, and this is shown on an oscilloscope trace by a straight line. Remember, the wave pattern is for AC, alternating current. So trace X and trace Z just show that the output voltage is constant over time. So my answer here is trace X and trace Z. So that gives us the answer D, X and Z only. Question 12 says the graph shows how the voltage varies with current for 3 resistors X, Y and Z. So on the y-axis we have voltage in volts, on the x-axis we have current in amps. And you can see here that X is steeper than Y, which is steeper than Z. It then says a student makes the following statements using information from the graph. The resistance of resistor X is greater than that of resistors Y and Z. Well, to think about which resistor has the greatest resistance, remember, the steeper the gradient, the greater the resistance. So if you look back at the graph, we said that X has the steepest gradient, so therefore it does have a greater resistance than Y and Z. So we can say that one is true. Statement 2 says when the voltage across resistor Y is 2.0 volts, the current in the resistor is 2.0 amps. Well, if we look back at the graph here for resistor Y, you'll see that when we have a voltage of 2.0 volts, that matches up with a current of 2.0 amps. So that means statement 2 is correct. So we can put a tick next to that one. And lastly, the resistance of resistor Z is 0.25 ohms. Well, to find if that's true, we can do a V equals IR calculation to find what R is. Well, looking back at the graph for resistor Z, we just need to choose a point on the line here. So let's choose the point here at the end, 4.0 amps along, and 1.0 volts up. So using V equals IR, we can sub in our numbers to get 1.0 is equal to 4.0 times R, and dividing both sides by 4 gives us 1 over 4, which is the same as a quarter, or 0.25 ohms. So that means this third statement is correct. So you'll see we have all three statements correct here, which gives us the answer E. Question 13 says, in which of the following circuits would the readings on the meters allow the resistance of R2 to be calculated? Well, to find the resistance of resistor R2, we need to know the voltage across R2 and also the current flowing through the resistor, so that we could use V equals IR and rearrange for R to find the resistance. So if you look at the first circuit, we've got an ammeter which is in series with the resistor R2 and a voltmeter across it. So A here would actually allow us to calculate the resistance of resistor R2. So that is going to be our answer. But let's see why the others are not going to be suitable. Well, if we look at B, first of all, you'll see we have a voltmeter in series with resistor R2, but that's not how we connect voltmeters into circuits. We put them in parallel with components. For C, we have an ammeter in parallel with resistor R2, but that's again not how we connect ammeters in a circuit. We connect them into the circuit. So that one's not going to be possible. For D, you'll see that we have a voltmeter across resistor R2, which is good, but then you'll notice our ammeter is actually in series with resistor R1, not resistor R2 here. So that's going to get the current flowing through this branch, not through this branch. And for E, that's just completely wrong because we've got an ammeter in parallel with resistor R2, which just isn't possible. And we've got a voltmeter connected in series here, which is just not how we connect voltmeters. Question 14 says a heater is immersed in a substance. The heater is then switched on. The graph shows the temperature T of the substance over a period of time T. So we have temperature in degrees Celsius on the y-axis and then time in seconds on the x-axis. And you'll see we've got this heating curve pattern here, which is sort of a zigzag or stepped pattern. And the question says which row in the table identifies the sections of the graph when the substance is changing state from a solid to a liquid and from a liquid to a gas. Well, remember on a heating curve, the changes of state are going to occur when the temperature remains constant. So we've got two sections where temperature remains constant here, which is Q to R, and then from S to T. And that's shown by the horizontal lines there on the temperature against time graph. So we could say that at point P we've got a solid, and we can heat up that solid until at point Q it's going to start melting, and then it's going to have completely melted into a liquid at R. So between Q and R we have our solid melting into a liquid, and then at point R we can heat up our liquid this time until at point S it's going to start evaporating until it reaches T, at which point all of the liquid will have evaporated, and therefore we have S to T is going to be our liquid to gas. So we can say that solid to liquid is QR and liquid to gas is ST, which gives the answer B. Question 15 says a sample of water is at a temperature of 100 degrees Celsius. The sample absorbs 9.0 times 10 to the 4 joules of energy. The mass of water changed to steam at 100 degrees Celsius is... Well, this question here is to do with specific latent heat, and in particular we're thinking about specific latent heat of vaporization because we've got water evaporating into steam. So we can use our equation EH equals ml to find the mass m. So writing down EH equals ml, you'll see I'm writing mlv for vaporization so that I make sure I'm using the correct value from the datasheet. So substituting in our numbers, we have 9.0 times 10 to the 4 joules for the energy given in the question is equal to mass times 22.6 times 10 to the 5. And remember that's our value for latent heat of vaporization for water on the datasheet. So dividing both sides by 22.6 times 10 to the 5 gives us mass is equal to 0.040 kilograms. And that is the answer B. Question 16 says a solid rectangular block is placed on a flat, smooth table as shown. So we've got our block there and the dimensions shown and it's sitting on a table, and it says the weight of the block is 28 newtons. The pressure exerted on the table by the block is... Well, in order to calculate pressure, because we've got a force here which is the weight of 28 newtons, we can think about the equation P equals F over A, pressure equals force divided by area. But that means we first need to find the area that is in contact with the block. So to do that we can use the length of 0.2 meters and the breadth of 0.1 meters, because by multiplying those two together that will give us the area of the block that's in contact with the table surface. So to find the area we can do 0.2 times 0.1, which gives us 0.02 meters squared, and then we can use the equation P equals F over A, and substituting in the numbers we have 28 newtons for the weight of the block, which provides the force in this case, and that's divided by 0.02 for our area, and putting that into your calculator should give an answer of 1400 pascals, which is option D here. Moving on, we have question 17. A gas is contained inside a sealed syringe. The volume of the gas in the syringe is decreased. During this time, the temperature of the gas is unchanged. This change in volume causes the gas particles to move faster, hit the walls of the syringe less often, move slower, gain kinetic energy, or hit the walls of the syringe more often. Well, if we think about the kinetic model of gases, remember you've got particles moving about in a sealed container, and in this case the container is going to be the syringe, and we're told that the volume of the gas in the syringe is decreased. And with a constant temperature, that means the particles are going to have less space to move around in, and therefore they're going to hit the walls of the container, or the syringe in this case, more often. So that means our answer here is going to be E, they're going to hit the walls of the syringe more often. Question 18 says a liquid is heated from 22 degrees Celsius to 64 degrees Celsius. The temperature rise in Kelvin is. Well, to do these questions, you need to remember that a change of 1 degree Celsius is the same as a change of 1 Kelvin, i.e. the size of the units are equivalent. So that means to find the temperature change in Kelvin, we just need to find the temperature rise or temperature change in degrees Celsius, and that will be equivalent. So we can do change in temperature delta T is equal to T2 minus T1, which is our 64 minus 22, which gives an answer of 42 degrees Celsius. And that means our temperature change is going to be the same as 42 Kelvin, which is A. Question 19 says 5 water waves pass a point in a time of 10 seconds. Which row in the table shows the frequency of the waves and the period of the waves? Well, because we have the number of waves here, 5, and the time of 10 seconds, we can use our equation relating frequency, number of waves, and time first of all. So we have F equals N over T. Substituting in the numbers, we have 5 divided by 10, which gives us 0.5 Hz for the frequency. So that's going to be options A and B here, and we can rule out C, D, and E. And then to find the period of the waves, remember we have an equation relating period and frequency, and we've just calculated frequency, so we can use that answer in our next equation. So we have T equals 1 over F, substituting in the numbers gives 1 divided by 0.5, and putting that into your calculator should give you an answer of 2 seconds. So that means we have 0.5 Hz for the frequency and 2 seconds for the period, which gives the answer A. Question 20 says a ray of red light travels from air into a glass block. Which row in the table shows the effect, if any, on the wavelength and speed of the red light as it passes into the glass block? Well, if the light's going from air into glass, then it's going to go from a less dense material into a more dense material. And remember, when light does that, it's going to slow down. And more specifically, the light's going to decrease in speed from the speed of light in air, which is 3 times 10 to the 8 meters per second, to a speed of 2 times 10 to the 8 meters per second in the glass. And so we know that the speed's going to decrease in the more dense material, and we should also know that from the equation V equals F lambda, the wavelength should do the same as the speed. So if the speed is decreasing, remember the wavefronts of the waves all bunch up as well. So that means the wavelength decreases for light when it enters a more dense material. So we should have that the wavelength decreases and the speed also decreases, whereas the frequency of the light, remember, always stays the same. So in this case, our answer is C. Question 21 says which of the following diagrams shows the path of a ray of red light as it passes from air into a glass block? Well, to help us answer this, we need to remember that when light goes from a less dense material to a more dense material, it bends towards the normal. So you'll see in diagram A here, when the light comes in, it bends away from the normal, not towards the normal. For B, you'll see the light just goes straight through. For C, you do have the light bending towards the normal. For D, you've got the light bending so much that it goes along the normal when it enters. And then for E, you've got this ray obeying the law of reflection, this reflection going on. So it's not going to be that one. So that means our answer is going to be C here, because that's the one that shows the light bending towards the normal, but not so much that it makes it go along the normal like this one in D. And a good check is to check that the angle of incidence should be greater than the angle of refraction for light going from a less dense to a more dense material. Question 22 says a uniform electric field exists between two oppositely charged parallel metal plates. An alpha particle, a beta particle, and a gamma ray each pass between the metal plates. They follow different paths as shown. So you've got X curving up towards the positively charged plate, Y going straight through, and Z curving downwards towards the negatively charged plate. Then says which row in the table shows the types of radiation that follow paths X, Y, and Z. Well, if we think about what alpha particles, beta particles, and gamma rays are first, remember that alpha particles are made up of 2 protons and 2 neutrons, which means they're positively charged, because the positive charge from the protons contributes to the overall charge here, and the neutrons are neutral, so they don't contribute. We then have beta particles, which are fast-moving electrons, and these are therefore negatively charged, since electrons are negatively charged. And lastly, gamma rays, remember, are high-energy electromagnetic waves, which means they have no charge since they're waves. So if we look back at the picture here, it's got to be the negatively charged beta particles, X, which are curving up towards the positively charged plate. Gamma rays are going to pass straight through because they have no charge and they're therefore not going to be attracted or repelled away from any of these plates. And then we have Z, which has got to be the alpha particle, which is positively charged and is therefore being attracted downwards to this negatively charged plate. So we therefore have beta, gamma, alpha, which is the answer D. Question 23 says, during ionization, an atom becomes a positive ion. Which of the following has been removed from the atom? Well, this is just testing whether you know the definition of ionization from the radiation topic. And remember, ionization is defined as the addition or removal of an electron from a neutral atom. And this will create a positive or a negative ion. And you'll see here it becomes a positive ion. But that's not needed to answer the question. It's just asking which of the following has been removed from the atom. So it's got to be A, an electron. Question 24 says a Geiger-Müller tube connected to a counter is placed in front of a radioactive source. So you see the source here and then the Geiger-Müller tube connected to the counter. The number of counts recorded in 1 minute is 3,890. Different shielding materials are now placed in turn between the source and the Geiger-Müller tube, and the number of counts per minute is recorded. So you can see that with no shielding material we get that number of counts per minute of 3,890. With a sheet of paper in the way, our number of counts per minute decreases to 2,110. With 1 centimetre of aluminium in the way, you'll see it doesn't really do anything to the number of counts, it's increased by 2. And then by using 5 centimetres of lead, you'll see the number of counts per minute drops quite a bit to 365. So it says the source is emitting alpha radiation only, beta radiation only, alpha and beta radiation only, alpha and gamma radiation only, or beta and gamma radiation only. Well, we can work it out from what's happening to the number of counts here. So we can start off with no shielding material, gives us this count rate, and you'll see that we're dropping quite a bit in terms of the number of counts per minute recorded when a sheet of paper is used. So that means the source must contain some alpha radiation because our reading is going down quite a bit using a sheet of paper. And that's because a sheet of paper, remember, can stop alpha particles. But when they use aluminium instead, we're not really getting much of a change in terms of our number of counts per minute. So that means that beta radiation is likely not going to be present in our source. And lastly, when lead is used, you'll see the reading drop quite a bit. So that means that gamma radiation must be getting stopped now. So that means our source must contain both alpha and gamma radiation, which is option D. Lastly, question 25 says, during radiation treatment, a patient's liver absorbs 90 microjoules of gamma radiation. The mass of the liver is 2.0 kilograms. The absorbed dose received by the liver is... Well, this is just a standard 3 marker where we need to calculate absorbed dose. So we're going to use the equation D equals E over M, energy per unit mass. Now plugging in the numbers, you'll see that I'm just going to keep the energy in 90 microjoules instead of converting that into 90 times 10 to the minus 6 joules. And that's because you'll see all the answers here are given in micrograys. So I'm going to save myself a wee bit of work by just keeping this in as 90. So we've got 90 microjoules divided by 2.0 kilograms for the mass, and 90 divided by 2 is going to give you 45. And we need to remember to put in the micrograys here. So our answer is 45 micrograys, which is option A. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.